Welcome, ladies and gentlemen, to Girton College. I'm the Mistress of Girton, Susan Smith, and it's my pleasure to welcome everyone here to enjoy the Founders Science Lecture, which is going to be delivered tonight by Professor Dame Pratibha Gai. Now, as well as being our first Founders Science Lecture, for which I'm very pleased to see so many wonderful and eminent scientists joining us, it's also the second lecture in a series of public lectures, of 5 public lectures that we're mounting to celebrate the foundation of Girton College 150 years ago. The College for Women, which is what it was at the time, opened its doors to 5 pioneering students in October 1869, and it's that pioneering spirit that has inspired these lectures that you're attending today. Now, it is true that neither of our principal founders were scientists. Emily Davis and Barbara Bodishan were, however, absolutely committed to the principle that all subjects in any university should be open to women, which they most assuredly were not in 1869. And they were determined that women should have the opportunity to study these subjects in the same way and to the same level as men. And that's why Lady Stanley of Alderley, and some of you are in the Stanley Library there, Lady Stanley funded the college laboratory that opened in 1877 at a time when women were banned from the Cavendish laboratory and from the lectures of at least 1 in 3 Cambridge professors. But our founders were certain from the start, you see, and of course they were proved right, that women could do just as well as men, sometimes even better. So it was that among the 700 or so students who passed through this college in the late 19th century, just under 10% were natural scientists and around 20% more were mathematicians, and the trajectory has continued upwards. For a flavour of those early days, after the lecture, I could invite you perhaps to look at some of our panels on some of our early scientists and other eminent scholars, and there are actually some panels around the history of the college that you might like to look at on your way through to the drinks reception, which tell you something about our early days. But just to give you a flavour, I've just picked out 3 early women scientists to give you a flavour of what went on. Hertha Ayrton, for example, was born in the 1850s. She was an engineer, a mathematician, a physicist and an inventor, and she gave the first presentation ever by a woman to the Royal Society. She secured the Hughes Medal for her work on the electric arc and the Sandra pores, and she registered no fewer than 26 different patents, which perhaps is not much these days, but at the time, I think it was quite a remarkable total. And like so many of her old Girtonian contemporaries, she worked tirelessly to give women who were excluded at the time equal opportunities in work, in society, in science, and of course in political and public life. And it's said that she, in fact, took part in all the suffrage processions of the early 1900s. Then there's Ethel Sargent. She was born in the 1860s, and she was a botanist, active in the botanical section of the British Academy, and is president for a little while. She was the first woman council member of the Linnaean Society, and she too was vociferous about women's engagement in higher education. She actually took on the presidency of the Federation of University Women. But she also established a tradition of excellence in plant science that flourishes in our college today, not least through the efforts of our senior fellow, Enid McRobbie, who's not able to be here today, but she has been a fellow of the college for 60 years. And she was the first woman scientist in Cambridge to be awarded a personal chair. She was the first female head of the Department of Plant Sciences, and she secured a fellowship at the Royal Society at a time when few women were recognised in that way. And just as a last example, there's Dorothy Rynch, born in the 1890s. She was a mathematician. She was the only female wrangler, if that was the right word for her year, and a theoretical biologist. And her attempt to deduce protein structure using mathematical principles probably, as many of you will know here, met a few dead ends and a few rather tricky challenges in debate. But eventually, it did help identify the driving force behind protein folding. And no one here tonight will need me to tell them how important that has proved to be. So they were some of the pioneers. perhaps not household names, but they were brilliant women whose early success, I think, fully justifies the establishment of the Founders Science Lecture here tonight. And that foundation was just a start. By the 1960s, the natural science tripos was the largest in this college, and we've gone from strength to strength. Now, so far, we have no Nobel Prize winners. Indeed, I'm very grateful to Professor Sir Gregory Winter, Master of Trinity, for joining us tonight, not only because it gives me an opportunity to extend our very warmest congratulations to him, to you on your Nobel Prize last year in honour of your work on human therapeutic antibodies, and we were all so delighted to be able to join you and to congratulate you on that. So it's super that you're here to represent that Nobel group tonight, but also to remind me that Emily Davis, her ambition was always, as she put it, to achieve no less than that of our neighbours at Trinity. So we are on that way, we are on that route. Of course, we've gone on, and we've been proudly co-educational for precisely 40 years. That's something else that we're celebrating in this year of 2019. We're celebrating the fact that, still inspired by our founders, we're now known for working together as a community to make real difference to the world. But at a time when women are still and stubbornly underrepresented in the STEM subjects, it's quite right, I think, in our 150th year, to pause to celebrate the legacy and aspirations of the generations of brilliant women scientists that have walked under our tower and into that wider world. And among past and present members of the college, in fact, we have no less than 4 UNESCO L'Oreal Women in Science laureates. Now, these were awards set up precisely to recognise the outstanding contribution to scientific progress made by women researchers. And I have the pleasure of introducing tonight one of those award holders as our special lecturer. Professor Dame Pratibha Gai is a physicist and chair of Electron Microscopy at York University, where you're the founding professor of the JEOL, the JEOL Nanocentre. Professor Gai is a fellow of the Royal Society, of the Institute of Physics, of the Royal Society of Chemistry, of the Royal Microscopical Society, and of the Institute of Materials, Minerals and Mining. She's got no fewer than 300 refereed scientific papers in leading journals, together with 9 co-authored and edited books and journal issues. As well as being a Woman in Science laureate, she received the Institute of Physics 2010 Gabor Medal and Prize for Environmental Transmission Electron Microscopy, and recently figured among the Asian Awards for Outstanding Achievement in Science and Technology. Consistent with the values established by our founders, she's got a truly collaborative spirit. Indeed, having created a microscope capable of perceiving chemical reactions at the atomic scale, she didn't patent it, but freely allowed others to access the design. And she is, as you would expect from an OG, as we call them, a former Girtonian, a current Girtonian, an outspoken advocate for women with careers in science. So it's my great honour to invite Professor Dame Pratibha Gai, newly elected Honorary Fellow of this foundation, to deliver the Founders Science Lecture entitled Catch Me If You Can, Atoms in Action for Energy, Environment and Healthcare. Professor Dame Pratibha Gai.
Thank you all very much. Before I begin my talk, I would like to thank Professor Susan Smith for those kind words. I would like to, let me just see if it works. Yes, I would like to, first of all, say that, thank her for inviting me to present this Girton 150 Founders talk. It's my great privilege and honor to do that. And in fact, it's a great honor for me to return to the college where I was a graduate student of physics more than 4 decades ago. And it's also an opportunity for me to celebrate 150th anniversary of Girton College and thank Professor Smith for her outstanding leadership, which is continuously enabling Girton women to dream more and achieve more. I would also like to thank fellows of the college, let me see if it works, and the mistress for awarding me an honorary fellowship, for which I'm very grateful. And also thanks to Michelle Stanley for all her help. and also to Professor Archie Harvey, who is here tonight, and he was my graduate studies advisor at Cambridge. And so I would like to start my talk. It's called Catch Me If You Can. Can you all hear me at the back? Okay, so this is the title of my talk. Basically, Catch Me If You Can, Atoms in Action for Energy, Environment, and Healthcare. And these are the three key things which are important to each one of us. So we are funded by various people shown at the bottom here. The main funders are the Science Council, the EPSRC, and we have funding from University of York, EU, and also various chemical and healthcare companies. And I'm going to talk about something about that later. And in fact, we have very good collaborations with the UK industry. So when I got admission to Girton, I was really over the moon. So it was a privilege to be part of the college. And after Cambridge, I moved to Oxford and then to United States, where I was at DuPont and Delaware for nearly 2 decades. And I returned to York as a professor of physics, chemistry, and electron microscopy, and also to co-found a Nanocentre to train students in advanced sciences. So that's the sort of background about Girton. But we scientists don't just sit in our labs. We get to go to all over the world because of conferences. So I tell my students, stay in science and see the world. And so that's what happens. So basically, as Professor Smith mentioned, Girton women have dominated science and technology awards. And as she mentioned, before me, there were Dame Donald and Dame Ashcroft. And I got it in 2013. But it says that it's a true statement in the award that science needs women. And so I tell my female students, to take scientific careers because they can do useful things to make this world a better place, like coming up with new drugs or new medicines, new energy sources, and new routes to climate control and so on. So thankfully, in our laboratory, the number of female students in science is increasing, so that has to be a good sign. So this is, after all, this is the International Women's Week this week, and so and women make up half the population, and more women scientists mean more benefits to the world. So that's my vision. So this is me and my machine, and that's the one I'm going to talk about. So atoms matter. Why do the atoms matter? Well, atoms make up everything, don't they? They literally make up everything. I mean, they are the basic building blocks of everything. And basic building blocks of matter, and so we need to visualize and analyze them to see how they work. So basically, my interest is to visualize and analyze atoms in action in chemical reactions. So, so let's take a look. Before we take a look, and I know that many of you are from different disciplines, so I've kept my talk very simple. So experts in the audience, my apologies. Okay, so let's take a look at the dimensions. What's a nanometer? Many of you may be familiar with nanoscience and nanotechnology. So what's a nanometer? A nanometer is 1/1000th of a meter. So an atom is 0.1 of a nanometer. So they are invisible to the human eye. Okay? So they're 1/10 of 1/1000th of a meter. So they are basic building blocks of matter. So they are fundamental to all reactions, including chemical reactions. So let's look at the salt here that we use every day. So this is the salt structure, and each atom here is 0.1 nanometer, and these beautiful columns it makes is about 0.2 nanometers. So these are the dimensions we are looking at, and in fact, a grain of salt can contain many, many millions of atoms. So we are trying to hone in on one atom, one at a time, working. And so when they're working, they say, they're moving around, they say, catch me if you can. So we have caught them with our development, and that's the story I'm going to present to you this evening. So here is the way I've shown it. These are the chlorine, and the green ones are the sodium. So that's how salt structure is made. And so this kind of gives you the sense of scale from nano to megascale. We start with the atom here, 0.1 nanometer. Multiply that by 1 billion times, you get a football, about 2 meters. And then similarly, you get diameter of the sun, which is about 1.4 million kilometers. So you can see the sense of scale here. And our planet Earth is here. It's really tiny by comparison. It's about 12,800 kilometers in diameter. So that kind of gives you a sense of scale. And we're right here at the bottom. And that is the fundamental building block. And so in DNA, for example, the diameter is about 2.2 nanometers. And you see lots of atoms inside. And silicon, which is fundamental to all the semiconductor technology, it's got atoms about 0.136 nanometers. So how to see them? We just go to wavelength and resolution criteria. And if you look at the right-hand side graph here, you have green light, which is the visible light, which is about 500 nanometers. If you go to electrons, let's say a voltage about 200,000 volts, the wavelength falls to about 0.0025 nanometers. So it's really very small, so it can resolve tiny objects. So, so we use electrons and we house them in a machine called electron microscope, very logical. And so, how to see them? How difficult can seeing atoms be? It's the same as looking at these little golf ball on the surface of the moon from the planet Earth. Can you see it? So it's as complicated as that. So I'm going to explain that with the little cartoon here. This is our moon. Okay, so that's our tiny golf ball, 4 centimeters diameter, and this is a beautiful planet Earth, and we're trying to see it from a planet Earth to the moon. What's the distance? 400,000 kilometers. So seeing a single atom like this in our microscope is the same as looking at a 4 centimeter golf ball on the surface of the moon from the planet Earth. So you can see that's the complication we have. So, so basically, many of you, have you ever wondered about the energy you use, the medicines you take, the food you eat, and the environment you live in, and all the immediate chemicals used in our everyday life come from? They come from chemical reactions. Okay, chemical reactions are basically reactions between different substances, and it's basically like making a cake. You put all these things and you want a cake at the end. That's exactly what we want. We want a desired product, a selective product at the end. And all these things, energy, healthcare, food, environment, chemicals, they all depend on chemical reactions. Chemical reactions are alive. They're constantly changing. They're like humans, so we call them dynamic. So these chemical reactions are speeded up by materials known as catalysts, and we call them catalytic chemical reactions or catalytic reactions. That's the word I'm going to use. So these are basically metals on supports, these catalysts. So a metal can be on a support like that, or they can be simple oxides. So they basically speed up the chemical reactions. And so these chemical reactions, to make matters complicated, they take place at the atomic level. And so I try to unlock mysteries of the changing atomic world in these chemical reactions to understand the reaction mechanisms at the atomic level. And this fundamental understanding is critical to develop new medicines, new energy sources, cleaner environment, and also improved products for the benefit of humanity. And we use modified electron microscope as a key tool to do that. So that's what I'm going to say. So let me just take my jacket off. It's getting a little bit warm. So basically, catalytic reactions, they help to convert cheap stuff into valuable stuff and clean up the bad stuff. They take place at the atomic level, and as I said, they impact heavily on daily lives, energy, medicine, food, etc. So the relationship between the dynamic atomic structure of the catalyst and the property are at the heart of these reactions. And so catalysis is extremely important. As you can see, it contributes something like $10 trillion into the global economy, and catalysis is very strong in the UK. All these chemical companies, Johnson Matthey, BP, Shell, have operations in the UK. So we have very good relationship with these companies, and we have collaborations with, especially with Johnson Matthey. So it's striking to note that everything is based on just 91 types of atoms arranged in different combinations. So that's really striking. So all the world is made up of just 91 types of atoms arranged in different ways. So basically, we are interested in synthesis, dynamic atomic structure, and properties. And today I'm going to talk about gas molecules and solid catalyst interactions at operating temperatures at the atomic level. We have done liquids as well, but I don't have time to do that. And here, basically, we are interested in understanding what are the intermediate phases during the reaction, because intermediate phases under reaction conditions may be critical to the reaction. So we want to understand that. So basically, we need a new tool, right tool for the job. See what this elephant is doing. It's basically drilling a hole at the back of the van to get at the food. And so this kind of gave us an idea, which I'm going to mention in a few minutes. And so basically, we need an electron microscope which can operate under gases, temperatures, and liquids at the atomic level. So in other words, we need an atomic resolution environmental electron microscope. We call it atomic resolution ETEM. So So, but there is a problem with the microscope, not with the elephant, because the problem with the microscope is that conventional machine operates in high vacuum, which means no environment. It operates at room temperature normally, and therefore, we can't. It's basically a static reaction. But as I mentioned, the chemical reactions take place in gas or liquid and operating temperatures, and so we simply need to have an atomic resolution microscope which can enable to do that. But atomic resolution environmental microscope was not possible, it was not available, and also it was thought to be difficult or impossible to attain under high gas pressures and high temperatures. So what's the solution? Build your own. So that's exactly what we did. We designed and constructed our own atomic resolution environmental microscope, to operate in liquid, gas, and temperature environments. I mean, there are risks in doing this at home because something may go wrong, but it's just a series of logical steps well managed. So, and one has to take some intelligent risk to advance science, as most of you know. It's just like crossing the road. It's dangerous, but you have to cross it to go from A to B. So that's exactly what we did. So I know there are some experts of electron microscopy in this audience, but I'm just going to mention a little bit about electron microscopy to some of the people who don't know. Basically, in the electron microscope, we shine a beam of electrons onto the sample. This is our object, and this is transmitted through, so we call it transmission electron microscope, TEM, very logical, and we detect these scattered electrons to form an image of the object. It's just like in a light microscope or in your camera. And so during this interaction, we also get X-rays, and they are characteristic of the elements in the species. For example, it can tell us what these atoms are, when they are sodium or chlorine or copper or whatever. So combination of that is very important to have both structure and composition. And we can also basically scan a probe of electrons onto the sample, like that scanning, and collect these highly scattered electrons. And in this case, the intensity is approximately proportional to square of the atomic number or proton number. So for example, if you have platinum on carbon, if you square it, you can see platinum is going to look very bright. I'm going to give you some examples later on. And so many people, many researchers have used this conventional microscopy to do atomic structure imaging, composition, and structural modifications called defect, etc. Very nice work, but unfortunately, we need these under reaction conditions. So that's the challenge. So, so basically, this is our electron microscope. In a standard configuration, it has high vacuum and room temperature, but we want to have chemical reactions under gas environments, under in situ conditions, under heating, etc. So that's what we need to do. In other words, we need to incorporate all these signals, imaging, diffraction, chemical composition, gas, temperatures, mass spectrometry to analyze the reactants and the products, everything in one microscope. So that was the challenge. And in the beginning, I had worked on in situ microscopy at Oxford. I built a reactor, which is something like that. I could put it in the microscope, connected various gases, and the machine was 1 million moles, and it was like 20 meters tall. And so every time I had to do the experiment, I had to put it in, put the gases and do the reaction and take it out, etc. It was really a pain. And, but I went to the nanometer resolution, which was the best at the time. And so we could publish it in good papers. And it also showed us that you have to have reaction environment to see the reaction. If you take it out in a vacuum, you wouldn't get it. So all the changes occurred under gas and temperature environments. But nanometer resolution wasn't good enough, so we needed atomic resolution before anybody else. We wanted to be the first. So that's what we did. We built the first atomic resolution. We were in DuPont at the time, under controlled gas and temperature environments, to look at the reactions in real time as they're happening, and also analyze them at the same time. So, and in York, we have then added both the TEM and the STEM configurations, as I mentioned earlier, and also what's known as aberration correction. This is correcting aberrations of the electron lenses. I'll come back to that a bit later. And this allowed us to look at single atoms in action. And these developments actually paved the way for atomic resolution studies of gas-solid reactions and opened up a new field of research worldwide. So if you take some risks, it can pay off. So the American Chemical Society, this was when we were young, highlighted our work, and it gave us a lot of publicity. So here we are. So I'm going to talk about the electron microscope modification, how we did it. And so, as I mentioned, remember the elephant, it was drilling a hole at the back of the van. So it's exactly what we did. This is our imaging lens shown in green here. So we incorporated holes to pump high pressure gas into the electron microscope. And, and also I was fed up of putting an ex situ cell. So what we did was use the reactor itself as the sample chamber itself as a chemical reactor. So that basically saved us using an ex situ cell, because if you put an ex situ thing, unless it fits extremely well, you will have some slack and some blurring of the image. But here, by using the chemical sample chamber itself as a chemical reactor, we could make everything very stable. And, and also you can see these red ones are apertures. We basically differentially pump the gas so that gas does not leak into the electron microscope source, which is under vacuum. So we didn't change the whole thing, whole microscope column here, and basically built a new microscope. This is the end product. You can see you can put high heat and gas, do the electron microscopy and chemistry at the same time, and you can put 4 gases together and, and watch what's happening and videotape it, or record it on a CCD camera. So it was all, and for the first time when we switched it on, we saw atomic structure changing. So that was like a eureka moment for us. So everything worked fine. And so these are basically the key features. Holes through the objective, imaging lens, 4 pieces, and we use the sample chamber itself as the reactor. It's a gas flow reactor, just like in technological reactor. It's a differentially pumped column, as I said, so everything is pumped around the chemical reactor, but the electron source actually is in the vacuum. It's a hot stage. We can heat the sample from room temperature up to 2000 degrees centigrade, and we always do calibration studies. And as the mistress mentioned, we did not patent it because we wanted to make it available to all researchers. So, in fact, our original atomic resolution ETEM is used for commercial production by FEI, who are the major electron microscopy manufacturers. And you can see all those models, including the 2018 models, are based on our development. And people are using it worldwide in USA, Japan, Europe, and China, and doing excellent scientific research. It's bringing both scientific and economic benefits, and also it's provided jobs for researchers, and hundreds of papers have resulted from it. So atomic resolution ETEM has also inspired gas. Now people are trying to put gas in a holder like that, but they have some limitations and they can't get single atom resolution. So in fact, our work has been publicized by all these scientific societies, Materials Society, ACS, etc. So it's received a lot of publicity. So in addition to building these microscopes, we have also, along with other people, invented some processes in catalysis, in high temperature superconductors, coatings, etc. And I'm going to give you a couple of examples of coatings. And one is for titanium. And this is titanium structure here, titanium dioxide. You can see oxygen are the red ones and the yellow ones are titanium. And this is used universally in all these applications, as you can see here. Coatings, paper, foods, strong polymers, healthcare, and cosmetics. And healthcare, all the pills, they are white because it's got titanium in it. It's a non-toxic material, but it is very active under sunlight. So if you put it in the sunlight, it becomes gray, and nobody wants gray paper, right? So what they do is to coat it with ceramic coatings like alumina and silica, and it stops the sunlight getting to the TiO2. But what they were doing before was to use a wet process. Basically, they would dip thousands of gallons of, a million ton of the TiO2 in hundreds of thousands of gallons of sodium silicate and sodium aluminate. It's a wet process and dry it out. And obviously, it's environmentally unsustainable and very expensive. So we said, can we come up with a dry process in our environmental microscope to put a nano coating without the wet process? And after one day, just one day of trying, we came up with this beautiful coating at one temperature. And this shows part of that. You can see coating of alumina and silica. We can get chemical analysis to confirm that. And TiO2 is in the middle. This is the titanium peak here. So it is now commercialized. It's called R350 pigment. It's used worldwide, okay, because it's everybody's house, cars, etc. depends on this painting. So on this TiO2, so it's used worldwide, and it's brought a lot of economic benefits around the world. And this was our patent, and it's commercialized now. And so you can use the environmental machine to invent new things. So it's been also publicized in the Materials Society Bulletin Intersections. And so these are some of the advantages of inventing these processes using our environmental microscope. The other thing we have done is to come up with solid coatings for vitamins, etc. You might have seen fish oil, which is a liquid, is underneath a solid coating. And we came up with that technology. And you can see we use basically titanium and silica solid coatings to put probiotics, antacid, antibiotics, pain relievers in liquid form inside these pills. And these are our patents, and healthcare technologists are actually using it. So environmental microscope not only can give us fundamental understanding, it can also lead to societally beneficial processes. So I returned to York, and I co-founded the Nanocentre at York. And basically, it's been very successful. Hundreds of students have been trained in advanced nanosciences in the Nanocentre. And at the same time, because all the students in the northeast of Britain, they were doing theory, but as soon as we set up this experimental lab, they all came to do the experiments. So it shows you students are really interested in experimental science. So at the same time, we also developed what's known as the double aberration corrected E-stem. I'm going to explain that in a minute. It allows us to look at atoms in action. Here, we basically utilized lens aberration corrections that have been reported in the literature in the past decade. I mean, electron lenses have aberrations just like humans. So they came up with the idea of correcting these lens aberrations, and we incorporated that. And so this is shown here. Without aberration correction, the electrons don't focus. So you have some aberrations here, but as soon as you put aberration correction, it can focus very well, and you can see the resolution is improved. So it's basically like Hubble Mark II telescope. So in our York machine, we have incorporated both the transmission and the scanning, and it's got aberration correction. And this gives us less than 100 picometer resolution. And under gas and temperature environments, basically under operating conditions, it allows us to visualize atoms in action. So because these are unique instruments, they are on covers of several journals. A couple of them are shown here. This is our E-stem, as I showed earlier, and this is our York machine. And so this is what our York machine looks like. We call it York E-stem, S-stem. And again, you see, these are the correctors, aberration correctors, and we chain the whole thing inside, and we also chain the pumping system. So it's really about 15 feet tall, 3 times taller than I am, and so gives us very nice resolution. These are silicon atom columns separated by about 0.136 nanometers. And you can see when we put the covers on, it looks really smart. And because it's only one of its kind in the world, we have delegations visiting us from America to Australia and in between. And so we have Thailand delegation here. And nice thing about that was half of them were women scientists, and they're all happy and smiling. So let me just give you some examples. This is gold. And when you take gold to the nanoscale, theorists predicted that it was round, but it's anything but when you look at them in experiments. So it's not round, and also it's got tiny defects. I'm going to come back to that in a minute. That's why I like experiments. You know, I'm an experimental scientist. For me, seeing is believing. So this is what experiment shows, and theory was supposed to show it round. So many people haven't an idea of catalytic chemical reaction, so I'm going to explain that in a cartoon. So this is, let's look at metals on supports in this case, okay? So, so let's look at the crystalline support. It can be amorphous support as well, but let's look at the crystalline support. And our environmental microscope gives us tremendous insights into surface engineering. In fact, we can look at what is the reactive species, and also when metal is on a support like that, how does it, where does it go, for example, and if there is a gas molecule sitting on it, how does it interact? And so after a while, these catalysts are like people. After a while, they say, I don't want to work, I'm tired. But they can't afford to, because if you stop a reactor, even for a day, it can cost millions of pounds in money. So we have to understand very quickly what's the problem, whether it's due to leaching when a component comes out, or whether it's due to sintering, where small particles are actually joining to become a big particle. So that's called sintering. So for example, imagine all these single atoms become a clump, you will lose the surface area and the catalyst deactivates. So we need to understand all that. So in the next video, in the real-time video, you'll see how the small particles like this become large particles. This is a real-time video. This is a platinum on carbon, and you can see very beautifully how this becomes large and sinter. And we need to understand that to optimize the process. This kind of tells us which actually planes are also involved in the reaction. There's this plane, that plane, and that's very important for us to understand and optimize the process. So for the first time, we have been able to look at these things at the atomic level. And so as I mentioned in our instrument, we have both transmission and the scanning. And as I mentioned here, in the E-stem, we basically have square of the intensity. So if you have platinum on carbon, platinum looks really bright on a carbon support. And you can see here, it looks like beautiful stars in the sky. This is our student's work. He's colorized it. You can see very clearly where the single atoms are. And these are rafts and particles around it. So this is in a platinum carbon. And platinum carbon is very important in fuel cells. Fuel cells basically convert potential energy of the fuel into electrical energy through an electrochemical reaction. And we need to understand what happens at the atomic level. Before we built this instrument, nobody knew these atoms existed because they couldn't see them. And so you can see, we can analyze the one atom here, two atoms there, etc. We can actually count them. And fuel cells are important in power generation and also in your portable devices like laptop and computers and so on. So we need to understand and optimize their function. So these are, for the first time, giving us insights into how a fuel cell works. And here, for example, you can see in the next video how one atom becomes two atoms, becomes three atoms, and it's so dynamic. The whole exciting atomic world opens in front of us. You can see here, look at this particle, and the atoms are coming out. And so we can stop it and look at the video from the still. It's the same video. This is the particle here, 3 atoms here, 4 atoms here. So, but the bulk of the particle is actually not doing anything. So everything is happening on the surface. So, and again, they are disintegrating, forming a cluster. It's a completely dynamic process. So for the first time, we've been able to image these, and it's giving us insight into what's exactly happening. It's telling us that this bulk is not interacting very much. So basically, these particles are acting as a reservoir for these atoms and clusters on the surface. And when they give up these atoms, you can see the particle starts to become more and more faceted. So I'll come back to that in a minute. You can see that much more clearly here. Room temperature, no gas. With hydrogen gas, platinum starts to interact, as I showed earlier. And at 500, we get more ordered nanoparticles. They become much more faceted. And in fact, they've given up many of these surface atoms. So we can study all that at the single atom level. And we can quantify this, understand how many atoms there are in each column. I don't want to go into that. So basically, these atoms and clusters seem to be doing all the reaction, and the bulk is not doing anything. So it's leading to economical catalysts with just atoms and atom clusters with less metal. So you can imagine the consequences of that and the implications of that. So that's what we are doing with Johnson Matthey at the moment. So I'm going to give some examples of healthcare, energy, and cleaner environment. So let's look at the healthcare. So in healthcare, I'm going to give an example of a model system. We are working with the UK Healthcare Technologies, but some of these are proprietary. So I'm going to use a model system, N-acetyl-P-aminophenol, which is paracetamol. And basically, we rearrange a molecule, this molecule here. And current process actually uses sulfuric acid. Did you know that? The pain reliever uses sulfuric acid, but there's a lot of waste here. So we are trying to develop, using our environmental machine, a green, a clean process at low temperatures, heterogeneous process. So this is basically the rearrangement of the atom. You can see atoms, they are the same number of atoms, but we are rearranging them in a different way and on top of this catalyst. And this is the catalyst we have developed. This is zirconia, tungsten on zirconia, and we use different loadings, and we basically make it with ammonium metatungstate and zirconium oxohydroxide, and we basically look at it in our ETEM under real-time conditions. So you see, after about half an hour, this amorphous clunk becomes really crystalline. And at 700 degrees C, it becomes much more crystalline. You get zirconia grains and these atoms of tungsten and atom clusters as well. And zirconium, as many of you know, used for jewelry, but zirconia, when it's oxidized, is a very stable ceramic support, and that's what we're using here. And if you look at it very carefully, we have anchored all these atoms and clusters along the grain boundaries of zirconia. So I can show you in a colorized image. So all these tungsten atoms and clusters are basically anchored very nicely, and so they don't move around and sinter. So under these conditions, we get very good product. You can see almost 98% product. And so small clusters and atoms seem to play a key role in the function of this catalyst. And we're using the same technology to synthesize potent antibiotic nanoparticles for implants and surgery. So that's where it's heading. And the second thing I'm going to talk about is biofuels. And many of you may be familiar with biofuels. These are environmentally sustainable energy solutions, and they are renewable energy sources. And we call them from field to fuel, okay? And so many countries have set targets to replace some of the fossil fuels with biofuels and to combat climate change and energy shortages. And everybody's talking about climate change. And there have been several meetings of the House of Commons, and the UK target is about 10% next year. These are the transportation fuels. So we need more scientists to do that, actually. So we are doing our bit here. So we are basically using plant biomass and convert that into biodiesel. And our interest is palm, rapeseed plants, and grass and weeds. And so around springtime, you see a lot of these rapeseed plants, and that's the one we are using. And BP uses it quite a bit for their biofuel. And so what we do is, just like people, plants have triglycerides. These are the fats. So basically, we want to convert the fat into esters. These are fuels. So call them triglyceride transesterification. And current process is homogeneous, which is very expensive. So we are trying to develop economical green processes, and we've come up with this simple catalyst, magnesium hydroxide methoxide. And so before I go to rapeseed, I just want to, and after that we want to go to grass. So before I go to rapeseed, I just want to show you grass. We cut the grass and throw it away, but when we looked at it in the SEM, scanning electron microscope, see how beautiful it is. And these are the things which contain the fat, and we want to transfer that into energy. And so this is a little bit more complicated than rapeseed, so I'll show the rapeseed. It looks very nice, as you can see, beautiful striations. And what we do is to convert that in the presence of alcohol into fuel, and we get a little bit of glycerol. But glycerol is used as sweetener in cakes and things that you buy in your supermarket, so it's not wasted. So when we actually do the reaction in our environmental machine, we see these atomic scale defects, structural modifications, and we didn't know they existed, and without the machine, we couldn't see them. So when we actually correlate them with the performance, you can see in the presence of these defects, the performance is maximum. So by operating in this regime, we have been able to develop efficient nanocatalysts for biodiesel synthesis. So we are now expanding that work to grass. So let me just talk about hydrogen energy. And this is the nano gold. Did you know that when you take gold to the nanometer level, it becomes very active? Gold under bulk form is very inactive, right? So we have jewelry, etc., because it doesn't react with anything. But if you take it to the nanometer level, it's highly reactive. It reacts with water, air, carbon monoxide, everything, and it changes from beautiful gold into dull gray. And who wants jewelry in dull gray? So this is the beautiful layers of about 0.23 nanometers here, and we are trying to use it to produce hydrogen for hydrogen cars and for fuel cells and so on. And so this is the reaction we are looking at, converting carbon monoxide with water into hydrogen. This is a clean hydrogen, and so we want it for fuel cells, as I said, for power generation and also transportation fuel, hydrogen cars. And so what we do is to put gold onto Syria support. Syria is very strong support, and so we want to interact with at 225 degrees C. The lower the temperature, the more economical the process is because you consume less energy. So we want to then do real-time visualization and look at the atomic level in this reaction. And for the first time, we can actually see how these gold atoms interact. So we are working with Johnson Matthey on this development. So we like to build things. So this is what we built to make humidifier. So water is humidified, and the water vapor is then put in our microscope along with carbon monoxide, and we then interact and see what happens. So when we actually make the powder, they look, there are millions of grains. I don't know, I didn't bring the sample yet. So anyway, they have zillions of grains, and we have to make sure that we made the right thing. So we do the analysis, and there is gold here, and also there is Syria here. So we have made gold Syria. So then we want to know where does gold go? If it's the Syria, where does gold go? It turns out that, this is my student's work, and he has looked at various models, and he finds that this is the experiments and this is the theory. And if you look at these graphs, experiments and theory, they kind of match. And so basically, gold is actually knocking out the cerium atoms and going in their columns. So we find that about 4 gold atoms go into the cerium atom columns. So we then put water and carbon monoxide together, and you can see as soon as you put water, gold comes to the surface. It's very reactive with water. And you can see that gold clusters and atoms come to the surface. And you can also see gold atom dynamics. Lots of these single atoms and clusters are present under these conditions. This is initial. After 20 seconds, 1 minute, 1.5 minutes, you can see more and more atoms seem to participate in the reaction. We can confirm that with analysis here. And then when we actually correlate with the performance of hydrogen, it's very strong, almost 98%, 95% at 275 degrees, and around 90% at lower temperatures. So the performance also shows that gold clusters and atoms are incredibly reactive for hydrogen production. So cleaner environment is critical to all of us. So I'm going to talk about exhaust emission control, in this case diesel engines and petroleum engines. Exhaust contains carbon monoxide, all these horrible things, nitrous oxides, and also in diesel engine it also contains oxygen. So predictions are that, although people are talking about electric cars, but the predictions are that these diesel and petroleum vehicles are going to be around for a couple of decades or more. So we need to do something about the emission control from cars, from trucks, and from trains, which all use diesel fuel. So we have come up with diesel oxidation catalyst, again working with Johnson Matthey in this case. And so this is our car. The exhaust has all these horrible things. So we want to convert, for example, carbon monoxide into carbon dioxide on our catalyst. And so this is actually what the catalysts look like. And you can see this is a real catalyst, about 10 to 20 centimeters across. And the exhaust comes in over the catalytic converter, and then we get some of these oxidized products. And we want to convert carbon monoxide into carbon dioxide and nitrogen oxides into nitrogen. But so we looked at the fresh and aged samples. This is the bimetallic system, platinum, palladium, and alumina. And you can see after 30,000 miles of driving, the catalyst converter becomes very black. And so my student actually did some work on this. So immediately you can see it has both palladium and platinum have sintered a lot, but it doesn't give you all the atomic details, so we need to go to the atomic details. And it shows that in the fresh catalyst, the particle size is about 2.5 nanometers, and as you go to after 30,000 miles, they've grown to 11 nanometers. In other words, they have sintered and they have lost the surface area. And you can see in the next slide, very nice segregation of a species on this other metal. So when you look at the colored picture here, you can see something has segregated on top, So he's used high precision chemical analysis to show that the segregated surface is actually palladium and the core is actually platinum. So we see that palladium is very interactive with carbon monoxide. So these insights have given us opportunity to develop optimum dogs for emission control. So that's what we are working on at the moment. So again, I talked about metals on metal oxides supports and so on, but we can use oxide themselves as catalysts. And when the day was like today's, rainy day, I went to the microscope and got this beautiful image of a silicolite. And these are used as adsorbents in detergents, etc. I just wanted to show you how beautiful these structures are. And in technology, what they do is to use oxides to convert hydrocarbon to make various polyurethane intermediates, etc., synthetic fibers, and so on. So this is one of the catalysts, vanadium phosphate. And they also use some of these catalysts to produce chlorine-free refrigerant. So they put like thousands of tons of these catalysts in a reactor. So we need to worry about the reactor as well. These reactors are like 100 to 200 feet tall, and they can cost between 100 million to 200 million pounds. And so they have to work, just like the catalyst, they have to work continuously. So one day they noticed that it wasn't working very well, and these are the grain boundaries. The reactors are Inconel, which are made up of nickel, iron, and chromium, and they saw this grain boundary failure. So, obviously they couldn't destroy these reactors. They said, can your in situ machine do something for us? So we said, okay, we'll try it. So we took a little piece from the top here and looked at it in the machine. And yeah, you can see this is a real-time video. This is the grain boundary, and we put the same environment in our machine, and we begin to see how these grain boundaries then precipitate and crack. Exactly what they observed. But this was actually happening at 690 degrees C, and the reactor was supposed to be at 525. So immediately we saw that there were hot spots in the reactor. We told them, and it was they were able to save the reactor. So technological benefits have also resulted from the atomic resolution ETEM used to identify cause of grain boundary failure and cure. So in summary, we have designed and constructed atomic resolution ETEM for atoms in action in chemical reactions, and it's leading to new research, and I've given you examples of sustainable processes in energy, healthcare, and environment. In fact, as Nobel laureate Rosalind Yalow said, new instrumentation leads to new science, and I hope I've given you some examples of that. And in fact, both our machine and atomic resolution ETEM and the chemical process inventions are used for commercial production, as I mentioned, and they are being used by researchers worldwide. And basically, we believe in science for society. And these are our various co-authors, without whose help this would not have happened. So all these are my students and postdocs and their poster sessions where they basically exchange ideas, and our eSTEM here. And so I thank you for your attention.
Super. Well, the time is leaving us behind, so we probably should draw together the formal part of the evening. And just before I make a final vote of thanks to Pratibha Gai, just on a little bit on the arrangements. So one of the fantastic things about this lecture series is that it has enabled us to finish our new social hub and bar. It's a cafe as well, but tonight it will be a bar. So people who would like to join us for the reception afterwards, the social hub is kind of in that direction, and I suggest that you take one of two routes, either out of this door and immediately into the hub, or out of that door and just a little way round. There's another entrance to the hub, so that is the quickest way to get everyone into a position where they can enjoy a nice cool drink, because it is a rather hot room. So we'll do that afterwards. You will walk by, whichever route you take, some lovely banners that our archivist and a college historian have done around the history of the college. So please do feel free to pause there, or indeed to get a drink and come back. If you are dining with us tonight, there'll be some separate instructions later, but they'll all flow from being in the social hub, where we can have some more informal discussion. So if I could just say, I think our founders, their vision was to enable anyone, whatever their background, whoever they were, to, if they've got ability and enthusiasm and ideas and the energy to pursue them, to enable them to be their best selves and to do their finest work. And I think, if I may, Professor Gai, you embody that vision. And I would like, on behalf of all of us here, to thank you so much for coming today to share your ideas with us. Thank you.
Thank you.